Hello, my name is Adarsh and today we are going to learn 3 address code generation. 3 address code is a type of intermediate code which is easy to generate and can be easily converted to machine code. So we need to understand first, intermediate code is generated from source code and compiler use that intermediate code to generate machine code which is also said to be target code. So in this way, uh, source code is converted to machine code. So in this video, we are going to learn one of processes of intermediate code, that is 3 address code. Some other process of intermediate code are DAG, prefix, etc., which we don't need to learn in this video, because in this video we are focusing on 3 address code generation. So in 3 address code generation, we broke down our source code into separate instructions. These instructions can easily translated into assembly language. So in 3 address code, we use at most 3 addresses and one operator to represent an expression, and the value computed at each instruction is stored in temporary variable generated by compiler. uh, I hope everyone is familiar with the concept of variable, which is used to store a value. Now we will look at some examples. First, we have source code a equal to b plus c. So to convert this a equal to b plus c, we have to break this down into some variables. So we will store value of b plus c in variable t1, value of a in variable t2, and now we will equate both of them. So in this way we have converted this source code a equal to b plus c into this 3 address code. So, and this 3 address code can be further translated into machine code by compiler. And you can see that we have used only 3 addresses at most in each instructions. So you have to be very careful about this, to use only 3 instructions, 2 argument, 1 operator, or whatever you want to use. It depends on you, but we have to use on maximum 3 operators. Now we will see another example, a into minus b plus c. Similar to previous one, we store value of b plus c in variable t1, u minus t1 in variable t2, and we have computed value of a into value of t2 in variable t3. So in this way we have again converted this source code into 3 address code. So I hope you understand this. Now we will look at another example of if and else statement. So for if and else statement, first we have to write if a is less than b. Now we will go to next instruction, t equal to 0. This goes in else statement. If this condition satisfy, it will go to L, and L we have defined as t equal to 1. So if this condition satisfy, L goes over here in this instruction. If not, if t equal to 0, go to L1, then exit. So in this way, if and else statement works in 3 address code. So we have to write 3 address code for while loop now. So we have this source code over here. While I is less than n, struct t equal to 0, I equal to I plus 1. We have already initialized all lines L as if n is less than n, go to L2. Else go to L5, which is exit. So we have go to so we assume that our I is less than n, so we go to L2 and it goes to next instruction, I equal to I plus 1, it increment its value and it goes to next instruction, go to L2. So again go to L. So again it goes to L and this loop continues. So in this way we have created a while loop in 3 address code generation. So now we will learn about implementation of 3 address code. The 3 address code can be implemented as a record with the address field, and there are 3 ways to represent that: quadruple, triple and indirect triple, which we will learn further in this video. So first we will learn about quadruple. In quadruple representation, each instruction is divided into 4 fields: operator, uh, argument 1, argument 2, which are operands, and result. Uh, its advantages are easy to rearrange code for global optimization. One can quickly access value of temporary variable using symbol table, which we will learn in this video about symbol table. Disadvantages are contain lot of temporary uh, variables. Of course, we will use temporary variables to store values, and in quadruple sometime variable number of variable increases, so it stores a lot of temporary variables, so it takes storage and it makes our program slower. Temporary variable creation increase time and space complexity, as I said. So now we will see an example of quadruple representation over here, which is a equal to b into minus c plus b into minus c. So we will store values of u minus c, or we can say minus c, in variable t1, store value of b into t1 in variable t2, and minus c in t3, b into t3 in variable t4, and now we will add value of t2 and t4 in t5. Now we will put whatever result we will get in t5 in variable a. So in this way we have generated the 3 address code for above expression. Now we'll see how it is represented in quadruple representation. So first we will make column for operators, 2 operands and result. Now the first operation we have performed is minus, and operands are c, and value of this minus c is stored in variable t1. Now we have 2 operands t1 and b, and operator used between them is of multiplication, and its value stored in t2, which is t1 into b. Similarly, we do this for every uh, operation performed over here. So we have operand c, and operator used is u minus, and value stored in variable t3, and similarly t3 into b, value stored in t4, t2 plus t4, value stored in t5, and finally we store value or result of t5 in variable a. So now we will learn about another representation called triples. in this we don't use extra temporary variable to store result of any operation, because it takes extra space and increases our time complexity. So instead of that, when a reference to another triple value is needed, a pointer to that triple is used. So it consists of only three fields, operator and two operands. But there are some disadvantages of triples as well. Temporaries are implicit and difficult to rearrange code, and it is difficult to optimize because optimization involves moving intermediate code. When a triple is moved, any other triple referencing to it must be updated also. So in this case, if we move a triple, it we also have to update its referencing point. So in this case, it is very difficult to optimize uh, our intermediate code. So that's uh, that's it. Now we see an example of triples. So we have an expression over here, a equal to b into minus c plus b into minus c. So first we'll generate a three address code of this expression. So put minus c in variable t1, b into t1 in variable t2, minus c in variable t3, b into t3 in variable t4, t2 plus t4 in variable t4, and finally we put whatever result we have obtained in t5 in variable a. Now you can see over here the representation of triple. These are pointers which are written in hash columns, and these are operators, and these are two operands. Now pointer 0 points to value of minus c, and pointer 1 points to value of b into whatever value points to pointer 0. So we have value b into whatever value points to 0 uh, points to pointer 1. Now we have value of minus c points to pointer of 2. Now we have b into pointer of 2, which is minus c, which points to pointer minus 3, sorry 3, pointer 3. Now we have whatever value points to pointer 1 plus whatever value points to pointer 3, we add both of them, and that value points to pointer 4. Now in last we have variable a, which is equal to whatever value points to pointer 4, and that value is points to pointer 5. So in this way we represent triples. Now we will learn about another representation called indirect triples. This representation is an enhancement over triple representation because it overcame the problem of optimization of intermediate code, which is present in triples. But in this, we use an additional instruction array to list the pointers to this desired order. In this way, thus, it uses pointers instead of position to store results. This enables these optimizers to freely reposition these sub-expressions to produce an optimization. So we will see the example of indirect triples. We have an expression given over here, a equal to b into minus c plus b into minus c. For the given expression, we have a three address code over here. T equal to minus c, put value of b into t1 into t2 variable, put the value of minus c in t3 variable, and put the value of b into t3 in t4 variable, put the value of t2 plus t4 in t5 variable, and put the value of t5 in a variable. And like we made a table in triple representation, we make table in indirect triple representation as well. Pointer 14 points to the value of minus c. Pointer 15 points to the value of b into whatever value points to pointer 14, and similarly pointer 16 points to the value of minus c. Pointer 17 points to the value of b into whatever value points to pointer 16. Pointer 18 points to the value of pointer whatever value pointer 17 plus whatever value points to pointer 15. Now uh, for pointer 19, a equals to whatever value points to pointer 18, and that value points to pointer 19. Now the main difference is in indirect triples we have an array of pointers. So what these pointers do for us. So pointer 0 points to the pointer 14, pointer 1 points to the pointer 15. So here we have a pointer for each pointers. So in case we need to update any value, so we don't need to give this uh, pointer, because in that case we also have to update the value to which we are referencing to it. So that makes our whole uh, intermediate code complex, and we don't want that. So we use this pointer instead of that. By using this pointer does not have any referential referential reference. So uh, this pointer doesn't make our intermediate code complex. So that's why we use an array of pointers. uh, Now we have a question over here. Write quadruple, triples and indirect triples for the following expression, which is x plus y into y plus z plus x plus y plus z. The three address code for the given expression is: put value of x plus y in t1 variable, put the value of y plus z in t2 variable, put the value of t2 into t1 in t3 variable, put the value of t1 plus z in t4 variable, and put the value of t3 plus t4 in t5 variable. So here we have a quadruple representation of the question given to us. We have operand x plus y, and that value stored in variable t1, and similarly y plus z stored value in t2, t1 plus t1 into t2 stored that value in variable t3, t1 plus z stored that value in t4, t3 plus t4 stored that value in t4, t5. So it is simple quadruple representation, as we have seen in previous example as well. Now we will see the triple representation of the same question. X plus y points to the pointer 1. Now y plus z, and that value points to the pointer 2. And now whatever the value points to the pointer 1 into whatever value points to the pointer 2, and that value points to the pointer 3. Now whatever value points to the pointer 1 plus z, and that value points to the pointer 4. Now pointer 3 plus pointer whatever value points to the pointer 4, and that result points to the pointer 5. So in this way we represent triple representation. And similarly in indirect triple representation we make the table like a triple representation, and we use a separate array of pointer to point these values separately. So in this case, we don't have to uh, uh, give our value of pointer 14 to intermediate code generator for optimization. We will give this reference, so it will reduce complexity. Of course, this array of pointer increase some space, but it is very less compared to what quadruple does. So thank you. Have a good day.